This experimental demonstration, entitled Investigating the Properties and Applications of Thiol-ene Resins as UV-cured adhesives, is brought to you by your friendly neighborhood lab rats Samir Sathe and Dewan An from the Scott Polymer Dojo at the University of Michigan. The question we aim to shed light on is what are the compelling features of UV-curable thiol-ene resins that warrant their use as adhesives and unique medical restoratives. Before we start, however, in the interest of safety, make sure these experiments are conducted under appropriate supervision while handling UV equipment. Also make sure you have your gloves, UV protection glasses and lab coat on. To understand the temporal control afforded by thiol-ene resins, we pit them against better known adhesives. You'll need a 2-part epoxy glue, superglue and the thiol-ene resin. After preparing the epoxy mixture in a 1:1 ratio, apply it between 2 glass slides. Do the same with superglue, simultaneously. Similarly, apply the thiol-ene resin and shine UV light for approximately 5 seconds on the point of application. At the end of 5 seconds, the slides with epoxy come right off. The superglue is completely cured. The thiol-ene resin does equally well. But by temporal control, we mean to show that superglue, once applied, immediately begins curing. The thiol-ene resin, on the other hand, won't until such time is required, simply by shining UV light. To demonstrate spatial control, coat the thiol-ene resin between 2 surface-treated sheets of PET so that the cross-linked film can be peeled off later. Cover the coated surface with a patterned photomask and irradiate the exposed surface for a couple of seconds. Since the unexposed resin does not cross-link, it can be washed off with acetone to produce patterned adhesion for intricate applications. An interesting ability of these resins lies in their partial polymerization. Irradiating these resins between 2 surface-treated PET films with low-intensity UV light for a very short time results in partially polymerized films that are flexible and can be transported as rolls. At the point of use, the film can be peeled off, applied and irradiated for complete curing. An extended goal of this project is to develop UV-curable dental resins using these thiol-ene formulations. The well-known class of methacrylate resins show high shrinkage stress that leads to debonding of the resin from the tooth enamel, causing secondary caries. Also, lower conversion results in unreacted monomers leaching into the oral pathway, proving to be toxic. Thiol-ene resins, with their lower shrinkage stress, homogeneous network courtesy of step growth polymerization, and higher conversion thanks to tailor-made photoinitiators, can effectively overcome these issues. If these ideas in UV-curable polymer chemistry interest you, know that there are endless possibilities out there, so keep exploring.